Hello friends, welcome to Einstein. In the last lecture we discussed about time dilation and length contraction. Now we will solve a problem based on time dilation. So the problem is that there is a spaceship. This problem is about time dilation. So there is a spaceship which is moving in space with respect to Earth. Here is the Earth and we are observing on Earth this spaceship. So this spaceship is going with some speed v. Now there is an observer on Earth who will, for which we will assign a frame S, and an observer inside this spaceship. This is S prime. Now you know that what time dilation suggests, that the time interval elapsed in both with respect to the two observer will be different. So the time observed elapsed in this frame is t prime, delta t prime, and the time which is measured by this person on Earth is delta t. And from the last lecture you know that this delta t prime is related to delta t by this formula. Where v is the speed of the spaceship and c is the speed of light, and we said that the speed of light is constant in all the directions. So we just stated this statement that the speed of light is same in all the directions. So we will change this statement in our coming lecture. We will add something to this. So, and for what this lecture is about. So if you assume that in the spaceship you are in the spaceship for a period of 1 year. So delta t prime is 1 year because it is in the spaceship. So this is 1 year. We are taking the units here 1 year. So delta t prime is 1 year, and this delta t, we want to calculate this delta t, and so the formula should be 1 minus v square upon c square, and if you calculate this you will find that this delta t will comes out to be 1 upon square root of 1 minus v square by c square. This term you will always encounter while studying special relativity, and sometimes it's also said as gamma. So we will come to that in our coming lectures. So if we assume some cases, like first case, if the spaceship is moving with a very high velocity, which is 0.99 times the speed of light. So for this velocity you will find that this delta t comes out to be approximately 7.088 years. So in the spaceship the time elapsed is 1 year, but on Earth the observer, when he will come and return back, he will find that approximately 7 years have elapsed. Now for your surprise, just wait, take this v to be 0.999 c. Now there is not much difference between these two values, but when multiplied with the velocity of light, this value is exaggerated. So delta t comes out to be in this case as 22.36 years. 22.36 years. So now you are again surprised that when this spaceship is moving with such a high speed, then the time slows. On Earth 22 years approximately has elapsed, but in the spaceship only 1 year has elapsed. So this may surprise you. You will think that there is some problem with there must be a problem with the clock. It's like some mechanical fault in the clock. When people try to learn relativity in the start, so they think like that there must be some problem, like the inertia of the clock has increased, or there is some mechanical problem with the clock. That's why the clock is measuring a different time. But it's not just about the clock. The time really happens to be, the flow of time is slow in this frame of reference compared to this. So on Earth, actually the 22 years have already elapsed. If you come and meet your friend, then you will find that they have become older and you are still younger. Your age has just increased by 1 year, and your friends are 22 years older than you. So you will notice the effect of age on your friends. But the main thing is that this speed is not easily achievable. The fastest rockets and spaceship cannot even reach 1000 kilometers per second. So how this velocity c is much greater than these velocities of the current spaceship, which is 3 into 10 to the power 8 meter per second. With this speed, light is moving with a very high velocity compared to the ordinary speeds which we encounter in our day-to-day life. So our mindset is framed in such a way that we assume that time elapses in a similar manner, or with same interval of time elapses in all frames of reference. But that is not true according to the theory of relativity. So this is now a proved fact that the elapsing of time, the time interval gets shorter inside a moving frame. The clocks run slow. Everything, all the processes inside this frame must be slowed by the effect of time dilation is on everything happening inside this frame. Now there are some arguments by some people, and they say that they try to prove the theory of relativity to be wrong. So we will also see that. So it's not just about the clock or any mechanical thing, or it's related to inertia. The flow of time actually reduces. The way in which time elapses in the two frames are different. The time is slower in a moving frame compared to a frame which is at rest. In the past, there have been many attempts to prove that relativity theory is wrong. And even now, many attempts are being done. Many experimentalists and theorists are trying to prove that relativity theory is wrong, but all attempts have failed till now. So, we will also see some kind of attempt in this lecture. So, before that, let's take a case of a cart. This cart is moving in a straight line with some speed v, and there is a ball on this cart which has been thrown with some speed u. Now there is an observer here and there is an observer here. he is at rest with respect to the ground. This is S and this frame is S prime. So in the rest frame of this S observer, he will notice that the ball is going with an upward speed velocity u, but for this observer he will say that the cart is moving with a speed v and the ball is moving with a speed u. So we have to calculate the resultant velocity, because as this ball detaches from the cart, it is already having that velocity. When you jump out of a moving vehicle, then you know that you have the speed of the vehicle added to you. So this S observer will say that this ball is having two velocities, one horizontal velocity which is v, and there is another velocity which is u. So the resultant velocity is square root of v square plus c square. So this is what S will tell you. And for the S prime observer, he will say that the ball is only having the velocity u in upward direction. So he will see that ball is going in upward direction, while he will see that the ball is going with a different kind of velocity. It is at some angle. So now we will apply this to our to the problem which we discussed in the last lecture to derive the time dilation formula. So in the last lecture you saw that there was a train moving with speed v, and inside the train there is a source of light which reflects back with the help of a mirror. It goes up and down. This point is we will draw a diagram here. So there is an observer, this is S prime, and there is another observer which is S. So for S, we have seen that he will say that the light ray starts from a point, reflects back and come to this point. So he will say that this starts from A and goes to B and then returns back from B to A. But for this this is for S prime observer. Now what S will see? S will see that the light ray starts from a point A, goes to B and then goes to C, because the train has moved with some distance. Now draw a perpendicular, and this is D. So in the last lecture what we said, that the speed of light is same in all directions. But it's not the complete story. With this you have to we have already assumed one more thing, that it is speed of light is same in all direction and for all observers. Because if you apply this kind of situation in this problem, then for this S prime, light is going upward and downward, so it is having speed c upward and downward. But for this S observer, as soon as this beam of light goes out from the source, it is already having the speed of the cart, speed of the train, like this cart. So it has an speed c in upward direction and v in this horizontal direction. So this speed must be square root of c square plus v square. This is c square plus v square. But in the last lecture we said that this speed is c, and now we are saying that this is not equal to c, but this is square root of c square plus v square. So in the last lecture, how we can say that this how this speed can be c, because if we assume that this cart situation is working, then this must apply here. So this beam of light must be moving with square root of c square plus v square and not with the velocity c. So how this velocity can be c? This must not be c, but its value should be this. So in the last lecture we have already assumed that the speed of light is same in all direction and for all observers. So for s and s prime, both the observer, the light seems to be same, the speed of light seems to be same, which is c. So for s observer, the light is going upward and downward with the speed c, and for the s observer, light is going in this direction with a speed c and going in this direction with a speed c. So this is the assumption which is made in, this is the postulate of special relativity. So speed of light is same in all direction and for all observers. So speed of light is not relative to anything. But if we assume that relativity, Newtonian relativity or Galilean relativity works, then the speed of light must behave in the same kind of manner. And if we do the same calculation here, then what happens? Let's see this. So if we have the delta t prime equals to this twice of BD length, twice BD, or you can say that A prime B prime. So this is twice BD upon the speed which he will notice, which is c, and delta t equals the twice of AB divided by this new actually this is the old velocity, Galilean. So c square plus v square. So now we will calculate the ratio of these two time intervals. So delta t prime upon delta t will be equal to twice of BD upon c multiplied by square root of c square plus v square upon twice of AB. Now this will be equal to BD upon AB into square root of c square plus v square upon c. So now we have to calculate this BD upon AB. So BD upon AB. So this BD length is given by the speed of light. We are going to write all the things with respect to S observer. So BD is equal to speed of light c into delta t by 2. From here to here, the time taken by light is delta t upon 2. So this is c into delta t by 2. Now for this AB, now you can write this AB as this is equal to square root of applying Pythagoras theorem as AD square plus BD square. So first we have to write this. So this is BD upon AB is AD square plus BD square. So now this will come to be, we will divide numerator and denominator by BD, so it will come out to be AD upon BD whole square plus 1. Now this AD length is given by the speed v, the time in which the light beam goes from D to B is the same time taken by the train to move from this point to move from A to D. So V into delta T upon 2. So now we can find AD upon BD. So AD divided by BD equals, this bracket thing is present in both the cases. So AD upon BD comes out to be V upon C. So we can write here that this is equal to 1 upon square root of V by C square plus 1. So this we have calculated, BD upon AB. Now you can write it like this. So just put it here. So this implies delta T prime upon delta T will be equal to this BD upon AB thing. You have this square root of V upon C whole square plus 1 into, now if you divide this by C, then you will get this as 1 plus V by C whole square. So these two things cancel out and give you 1. So what we get is delta T prime upon delta T is equal to 1, that is delta T prime equals delta T. So this is what you get. So this is our result. If you assume that the speed of light is different for different observers, then we find that this delta T prime equals delta T. But if you from a start you assume that the speed of light is same for all observers in all directions, which we have already done, then in that case you will find that this delta T prime and delta T are not equal. So we have the final conclusion is that that if we assume that speed of light is same in all directions, then for the two observers the speed can be different. The speed of light can be different for two observers, and there is no time dilation effect. But if you assume that a speed of light is same in all directions and for all observers, then you will notice that this delta T prime is not equal to delta T in that case. So if delta T prime is not equal to delta T in case of C equals same in all directions and for all observers, and this is only for the direction case and not for all observers case. So now to accept that relativity theory is right, we have to do experiment, and in experiments we found that the time dilation effect is there. So time dilation is not a virtual thing, it's a reality which we do not perceive in our daily life, because for that we need very high velocities, and at very high velocities we observe the effect of time dilation. So, and for normal speeds in our day-to-day life, we do not, the effect of time dilation is so negligible that we just ignore it, and the Galilean transformation and Newtonian laws works well in those regime. So we come on conclusion that the speed of light is same in all directions and for all observers, because we have to satisfy the experimental results. So if experimental results are true, then the speed of light is not relative to any observer. So it doesn't matter with what speed or velocity an observer is moving. We will discuss some more cases in our coming lectures. So it doesn't matter with what speed you are moving in any direction, whether parallel or anti-parallel to the beam of light, you will always measure that the speed of light is always same, which is 3 into 10 to the power 8 meters per second. So speed of light is not relative to any observer. So this is a well established law in physics. So theoretically you can think in different manners. You can apply the Galilean results or transformation in these situations, but ultimately what we have to do is we have to explain what we are observing in experiments, and the experiments say that the effect of time dilation is a reality. So we cannot apply that cart and ball kind of thing here and write that this velocity c square plus v square is holding. This is not true. The speed of light is c for the two observers. So relativity is actually not proved wrong. So how we can assume that how from theory we can tell that this is working, that this speed is not c square root of c square plus v square, but this is c. So how from theory we can tell this? And for this, because the speed of light is same in all directions and for all observers, this was only established after the Michelson-Morley experiment, which we have to discuss in our coming lectures. But as I told you in the last lecture, that Einstein was a great theorist and he doesn't needed any kind of experiment to prove his theory. So he guessed from the laws of from the equations of electromagnetism, he thought that the speed of light cannot be with respect to any observer. It should be independent of any observer. So speed of light is constant for all observers in all directions. It is established by closely observing the equations of Maxwell, which Einstein did. And in the coming lectures we will see how Einstein thought and came on that conclusion that c is constant for all the observers. So we will come to that in our coming lecture. Please like our video, share our video and subscribe to the channel, and thanks for watching.